Good morning, everyone. So we'll be starting the session in another next 5 minutes. Okay. So please try to recall all the concepts which we have discussed in between. In the previous sessions. Thank you. Okay. No, no, no. Having yours. Okay, you're having network issue. No, till now the class haven't started, Nishu. And one more thing, so I see this query is come popping up. There was a session on Saturday. Started, okay. Didn't get any updates, so we have waited for an hour. Okay. Uh, Actually, that session was in a mentoring session. Should have been handled by the mentor. I'll just look through what happened on that particular day. So that will be a 1 hour session. Okay, on every Saturday from now onwards, and every Saturday you'll have a 1 hour session. Okay, I thought you people are aware of that. It's fine. So coming from this week, every Saturday you'll have a 1 hour session. Okay, 1 hour mentoring session. Whatever the topics which have been covered in that particular week, or else in the previous week. If you're having any queries on those topics, you can directly ask all the queries on that particular Saturday session. Okay, is that clear? And also Pulkit, is that clear, guys? No, the session wasn't cancelled actually, Pulkit. And don't worry about the attendance as the session haven't started on that day. Okay. Okay. So what were we discussing on the last day? So everyone understood the workflow of this NLP. Yeah. Everyone understood the workflow. Fine. Okay. Thank you. So I hope we can move further and we can start discussing this transformers architecture. So in that case, just a moment. Yeah, fine. Okay. So anyone know how these chatbots have evolved? How these chatbots have been evolved? What are the different kinds of chatbots which were in the picture? Anyone aware of it? Just give me a minute. Just a moment, please. Yeah, I'm sorry. Okay, I see one answer rule based, AI powered hybrid type. So, what is this rule based? What is rule based, guys? And have you got that NLP file, the notepad file? Were you people able to see it in your Telegram group? Just confirm me. In the meantime, I'll just share my screen. Okay, making decisions or perform tasks based on the predefined set of rules, or yeah, having predefined set of rules based on predefined. Okay, fine. Got it. So let me just share the screen and my notepad. Okay, fine. So I hope everyone is able to see the notepad which I have just drawn. So in earlier days, in around like 2000s or else 90s, so we used to have a rule-based chatbot. Rule-based chatbot. What exactly is this rule-based chatbot? We will be having a predefined rules, and based on those rules and the if-else logics, the chatbot will be acting along. Correct. So if you ask any query for that particular query, if they are having the answer, like if that a logic is written or else under the loop there is any answer accordingly to that particular query which is present, then it was giving us a reply. Correct. It is giving a reply. Even if the query which you are asking is not matching exactly word to word present in the rule based chatbot, so it will not be able to answer, right? It will not be able to answer. So that was the main issue with the rule based chatbot. Okay. So now, later after rule based chatbot, what happened was, how many of you know about this NLU? I mean, the major turnovers I'm saying. Right now, the major turnovers I'm saying. Then comes this NLU. NLU is natural language understanding, right? Natural language understanding. Under the natural language understanding, we have RASA chatbot. How many of you worked on this RASA chatbot? Anyone worked on RASA? See, when you're working on these chatbots, okay, when you're trying to build the chatbots, try to export this RASA chatbot documentation, okay? It's very clean, neat, and simple. RASA chatbot, okay? Clean, neat, and simple. In this RASA chatbot, we used to have intent, okay? Intent, okay? Intent. What is this intent? So, see, any question could be asked in different formats, right? See, the same question could be asked by four different people in four different formats. Correct. So the question could be like, if it is related to greeting, okay, greeting, then the questions will be, what are the different types of questions we can get, question formats we can get, which are related to greeting. So one could be, uh, like it could be general good morning. Correct. Okay, what are you up to this morning? Correct. Are you up to this morning? This is one kind of query. Or else, as it is related to greeting, you can directly say good morning, good morning, or else WhatsApp. I mean, in this present trend, most of the people will be using this kind of terminology, right? WhatsApp, and also a simple plain neat good morning we can consider. Good morning is already included, right? So, what are the other formats of greeting? How's your day going? Like asking, right? In a question format, how is your day going? Or else, there were many other formats in order to ask, or else in order to say good morning, right? Hope you're doing well. How are you? Yeah, how are you? Is kind of a question. So all these questions come under this greeting, correct? See, try to understand what I'm saying. All these type of questions will come under the greeting, right? Let's take out this first one. Okay? Let's take out this first one. So if you consider these two questions, they come under greeting, right? They come under greeting. So greeting is the main intent, okay? As I told in Rasa chatbot, we work with the intents. Greeting is the main intent, and under the greeting, we will have question and answer. Okay, question and answers. So these are some of the questions that user can come up with, and so for that, answers will be present. So for good morning, you can say the reply could be the same, right? Good morning. How are you doing? How are you doing? So this is one kind of reply to good morning. WhatsApp. For WhatsApp, we can directly say nothing much, or else we can directly say doing good. Such kind of replies we can expect, right? So For these two questions, these two are the answers for this intent. Okay. Each and every intent will have question and answers. And for each question, there will be an answer lined up. So if you are having around 5 questions, so 5 answers will be over here. Okay. Is it clear until now? Intent. I'll just explain in short about this intent. Okay. Just see. Intent means this thing, greeting. It could be greeting. It could be traveling. It could be related to recommendations. I mean, if you are building a travel chatbot, it could be related to travel recommendations, top 10 places suggestion, top 10 food streets. Correct. It could be related to as per the domain. It could be related to as per the domain. So here greeting is the intent. And for the greeting, we'll have question and answers. Okay. Question and answers. So earlier I told one single question can be asked in many formats, right? So now if user is asking a question and if that is being related to this greeting intent, any one of the reply will be popping up. Okay, any one of the reply will be popping up as per it will check for this similarity, and any one of the reply will be popping up. Okay, which is the closest answer for this, for the kind of the question the user is asking and what kind of intent it is belonging to, and it will be replying with this kind of an answer. Is that clear? Rasa chatbot NLU. Everyone. Okay. I see plain responses. Hope it's clear for everyone. Okay, fine. So, I'm not understanding anything. You're not understanding anything. Is this your first session? Jyoti Arnav, is this your first session? Yeah, I have seen your query, Arnav. So please keep all your queries to last 10 minutes, okay? See, the thing is, we were discussing about this history of chatbots, okay? We were able to discuss about this transformers architecture. Okay? So, and I was saying about Rasa chatbot NLU, which performs based on natural language understanding. Rasa chatbot, you can go and search in the Google also, you can get to find about this. This is a chatbot which is built on natural language understanding, and it works mainly on intents. Okay, intent means this is the intent, and each intent will have at least 4 questions and 4 answers accordingly. So let's say for this greeting intent we have 2 queries. So for each query there will be an answer, and according to the question which is being asked by the user in the chatbot, it will identify which intent does the query belong to and what kind of query he is asking about, and it will answer relatably. Okay, it will answer accordingly. So that is how the chatbots have evolved from rule based to NLU. Okay, rule based to NLU. This is how the chatbots have evolved. But later we got RNN based chatbots also. Everyone know how RNN works, right? RNN, how they work? In RNN, the order does matter, right? In RNN, the order does matter. So similarly, we got, but RNN was struggling with what kind of issue? You people needs to tell me. RNN is struggling with what kind of issue? RNN was having an issue, correct? Because of that issue only, LSTM got into the picture. But what is the issue with RNN? What's the issue with RNN? Remember anyone? Correct. Dhananjay, good one. Thank you. Yeah, vanishing gradient issue. Vanishing gradient is the issue. Yeah, they don't capture the long-term sequences. So in order to make sure that is happening, LSTM got into the picture. LSTM got into the picture. But even LSTM was having an issue. They were unable to understand the context. Okay? Context. So, in order to make sure even the LSTMs are able to understand, I mean, even the models are able to understand the context, then comes this transformers. Okay? Transformers architecture. Okay? Then comes the transformers architecture. And anyone heard of this transformers architecture? Transformers architecture purely work on self-attention mechanism. Okay, self-attention mechanism. Transformers architecture are purely designed to understand the context. Okay, purely designed to understand the context. To understand the context. Okay, transformers architecture purely designed to understand the context, and they work based on the self-attention mechanism. They work based on the self-attention mechanism. Is it clear now? Is my audio clear? Yeah, even BERT is also present. Bidirectional encoder. And this transformers architecture got introduced, or else it was introduced by Google. Okay, Google DeepMind in 2017. In 2017, through a paper, and the paper name is "Attention is All You Need." So this is a paper name. Okay, research paper name. Even you people can go and search for this research paper. Okay, "Attention is All You Need." This is a research paper name. "Attention is All You Need," and it was published in the year 2017 by Google DeepMind. It works based on the self-attention mechanism. Okay, self-attention mechanism, and we call it as a transformers architecture, and it is mainly used to understand the context. Is my voice audible? Everyone let me know, please. My voice was audible, right? Even I checked my internet also. It's working good. So please, Pulkit and also Pratham, please check your internet connection from your side. Okay? From my side, it's good. It's working now. No, it's not. Okay, fine. Fine. So just understand that in order to make sure in order to make sure the context is also being understood, this transformers architecture got into the picture, and it works purely based on the self-attention mechanism, and it will make sure that it is understanding the context. Okay, and all these things were published in the paper called "Attention is All You Need" by Google. Okay, by Google DeepMind actually. So it's a research team in the year 2017. Okay, so until now everything is clear, right? We'll just start discussing this transformers architecture in detail. Until now everything is clear, right? Rule-based chatbot, NLU, RNN, LSTM, transformers architecture. This is how the chatbots have evolved. And now whatever you're seeing, this ChatGPT, Gemini, Claude, or else Anthropic, all these chatbots that you're seeing, or else all these LLMs, they're working based on this Transformers architecture only. So understanding Transformers architecture is very important. Okay, fine. I'll just share my screen and I will also share the PPT. In the meantime, if you're having any doubts until now, let me know in the Q&A. Okay, now we are going to discuss about this Transformers architecture. Yeah, attention is all you need. Okay, let's move further. So agenda is in this particular PPT or else in this particular topic, what you will be learning is introduction to Transformers. I have already given introduction to Transformers. We'll deep dive into this Transformers. What are the key components of Transformers and understanding those key components. Okay, this is the main agenda of this Transformers architecture. Okay, and we'll try to close it off by today. So mainly Transformers. So while we're looking at the Transformers, what exactly Transformer is, just imagine it as in a black box for now. Okay, just imagine Transformers as in a black box. So this one is as in a black box for now. So input and output. So what exactly happening? What are the input query you are asking? It is going into the Transformers architecture, and the input is being processed, and you're getting a processed output. What it is saying? So transformers are also neural networks which are designed for sequence transduction tasks. They can transform an input sequence into the output sequence. Example, translating the language or summarizing the text. So based upon how we are planning to make sure the architecture is being built. Like for example, I want to build a transformers architecture where it will be summarizing the inputs. Correct. So that will be one kind of a transformer architecture. Or else I just want to translate them. Okay, I just want to translate them. Okay, those kind of queries. Those kind of queries. So like translating, summarizing, those kind of architectures we can build. So let's say if this is about this is related to summarizing. Okay, I just give an input, so it will be summarizing and providing the output of that whole input. Correct. So if it is related to translation, if I give an input, then all it does was what it does, it will just summarize that particular text, or else it will translate that into a different language and it will provide the output. And what language it will translate? It will translate to the targeted language. Correct. So just imagine this input will be I mean, just consider input will be passed into a transformers architecture and it will provide some output. Okay. So this is about the transformers. In the beginner, like as this is our very first introduction to transformers, just understand it that way. Whatever the task which we are assigning to it, it is able to solve. Okay? It is able to do that particular task. But what exactly present in the transformers? The key components of transformers. What are the key components? Encoder, decoder, positional encoding, attention mechanisms. So these are the main key components of transformers. Okay. Main key components of transformers. What are they? Encoder, decoder, encoding, attention mechanism. So what is happening over here? Encoder. There is an input. How are you? Which is going as an input to the encoder. And from the encoder, it is all the process is happening over here in between. And it is going into that decoder. And this encoder decoder is then a transformers architecture. And we will be provided with an output like in a different language. We are doing it language translation over here. Like how are you? Homo estas is a translated output. So how this input is being translated in this format? By using the encoder and decoder. And where are this encoder and decoder present? Inside the transformers? Okay. Inside the transformers, we're having encoder and decoder, which is taking the input and encoding it and passing it to the decoder. And decoder is decoding and providing us the output. And all this process is happening inside this transformers. Okay. So these are the key components. Remember encoder, decoder, encoding, attention mechanism. Okay. This is the complete architecture of transformers. Okay. Here you can see input sequence, embeddings, positional encoding, multi-head attention, adding and normalization, multi-layer perceptrons, again add and normalizers. So this is whole encoder architecture. And here comes the decoder architecture. What is this decoder again? What it is doing? Here, what are we having here? The target sequence, embeddings, again embeddings, positional encoding, masked multi-head attention, and from the embeddings, if it doesn't want to perform the mask, we can directly go for normalization, and then we can go for this multi-head attention. Then comes this normalization again. If you want to add extra normalization layers, then the multi-layer perceptron, then comes the normalization again, then the output of the decoded word, output of the decoded word. So from this whole image, from this whole architecture image, what did you understand? What did you understand? See, as per my understanding, if I am a new learner about this transformers architecture, what I will be understanding is there is an input sequence going into embeddings, and there is this positional encoding happening, and there is this whole encoder architecture. In this, some layers are present, and from the encoder, it is going into decoder, and in the decoder also some layers are present. Along with that decoder, we are having some target sequence embeddings also, and combination of that, we are getting a output, and on that output layer, there is this softmax function and the linear function which is being applied. So this is what I understood. If I'm learning new this transforms architecture, what did you people understand? What did you understand by looking at that architecture? Are you people understanding the same which I understood, or else are you people not getting anything? See, understanding this architecture is very important. Okay, see only one response. What about the people who are present? I mean, this is your first session. Manpreet and also a few others. Abhinav and also Vaishnavi. Okay, fine. Thank you. A bit confusing. Fine. See, for now, just understand that there is nothing present over there. Okay? Just a minute. Let me just make it clear. See, forget about that encoder. This whole block, forget about this whole block. Just say there is an encoder only. Okay? Only encoder is present. Forget about all these layers inside the encoder. Only decoder is present. Forget about all these layers. Just think like encoder and decoder as in a black box for now, okay? Black box for now. We don't know what's happening inside encoder and decoder, what layers are present. Okay. I'll try to switch to Hindi sometimes, but my Hindi is not that good, okay? I'll try to switch in between. And there is this output probability. Output probability means like whatever the output we are expecting from the input. Okay, there is this softmax. Softmax is an activation function, correct? Okay, so this is what we have understood now. And there is this positional encoding embeddings. We need to understand what is this input sequence, embeddings, positional encoding. First, we'll start with the encoder side. Okay, encoder side we'll start. For now, just understand input is going into the encoder. Some process is happening that is being sent into the decoder. Some process is happening, and we are on top of that. It is going into the softmax function, and then we are getting the output. So that is what is happening exactly. Fine. Now we'll start from the very first one, embeddings. Okay, embeddings. What is this embeddings? Embeddings. Okay, there is some embedding happening. Either it could be a word to wave or else any word embeddings which is happening. And then there is this positional encoding. Okay. So positional encoding means maybe encoding as per this position. As per the terminology, we'll understand. Okay. As per the terminology, it is encoding as per the position. So, but what exactly happening in these two now we'll see. Okay. Embedding means some embedding is happening. Some word to wave or else some kind of embedding is happening. We know embedding means as of now we know word embeddings only. Word to wake and also cgram, right? So some kind of embedding is happening over here, and after that, for each embedding, there is a positional encoding happening. Now we will see what exactly happening in these embeddings and positional encoding. Okay. Okay. So input sequence is present here, right? Let me just take this picture. It's not allowing me to copy that image. Just a minute. Just I'll just open this OneNote. Okay? I'll just open OneNote. It will be clear. I was not explaining multi-head attention. I was explaining the whole architecture kind of Srivaksa. Okay. Let me just share the screen. Okay. Now I think everyone is able to see the screen, right? Okay, fine. So now we'll discuss about this input sequence. Okay, input sequence. What is this input sequence? Input sequence is nothing but the input text that we are giving. Okay, input text that we are giving. So let's consider the input text that we are giving is the cat sat. Okay, this is the input text that we are giving. Okay, this is the input text that we are giving. Input sequence is nothing but the cat sat. Okay, this is the whole sentence. The cat sat. So in this input sequence only, we will have embeddings. Okay, the input sequence will be going into embeddings. But before that, how this input sequence will be, it will be divided into tokens. Okay, it will be divided into tokens. That is called token embedding. The first step is token embedding. Okay, I'll just write down over here. In the input sequence, we have token embedding. So now we are going to discuss about this token embedding. Okay. So what is this token embedding? I'll just write TE. Okay. Token embedding. So I told you, right, in the input sequence, this whole sentence will be divided into tokens. So what we'll get? How many tokens we'll get? How many tokens we'll get, guys? Yeah, three. Three tokens we'll get. So we are having three tokens. The cat sat. Okay, we are having three tokens, and on these three tokens, we'll do the token embeddings. Okay, on the three tokens, we'll do the token embedding. So in this token embedding, what we'll be doing is we'll be embedding each and every token. But before embedding, we need to make sure that, just confirm everyone, will the models will be able to understand the textual language? Will the neural networks be able to understand the text language? See, let's say you're building an ANN architecture, or else let's say ANN you're building. Will they be able to understand the neural network? I mean, will the neural networks able to understand the text language? No, right? They won't be able to understand the text language. So here we'll be having the token IDs. In this token embeddings, we have token IDs. Okay, token ID. So what is this token ID? For each and every token, an ID will be assigned. For each token, an ID will be assigned in the token embeddings. What is token ID and why token ID? See, these token IDs are necessary because neural networks cannot operate directly on the text, right? Neural networks will not be able to operate directly on the text. So they work with the numbers. Correct. They work with the numbers. And this token ID will be acting as a bridge. Okay. Will be acting as a bridge between the textual data and the numerical data. That's it. Token ID will be acting as a bridge between this textual data and the numerical data. Because the neural networks architecture will not be able to understand the textual data. It only be understanding the numerical data. Correct. So in order to make sure it is understanding this data, first we'll be assigning the token IDs. So the token IDs it will be assigning randomly. So let's say 101, 102, or else 205. Okay, these three are the token IDs which are assigned for the cat and sat. Okay, these three are the token IDs which are assigned for this the cat and sat. Understood why we need to do the token IDs? Why token ID is required? Understood? So now what 101 represent? 101 will be representing the, right? 101 will represent the, 102 will represent cat, and what was the last one? 205. Okay, ignore the writing. So 205 will represent the sat, right? The cat sat. Okay, I hope everyone understood until now. So what we did here, we can't directly give input as an text. So we have first, in the embeddings only, we have this token embedding. Okay, we have this token embedding, and on the token embedding only, what we did, we have embedded our tokens. How initially we have assigned the token ID. Correct, token ID. So the inputs are the cat set, the token IDs are 101, 102, and 205. Correct. So what will be the output shape for it now? What will be the output shape for those embeddings? See, for the, it is 101. cat. It will be a bit confusing here. 102 sat. It's 205. Okay. These are the token IDs which are assigned. I mean, it was embedded, right? It was embedded. So now, how many features will each token have? How many features will each token we are considering? For each token, we'll consider 512 features. Okay, 512 features. What are these 512 features? 512 features are nothing but the 512 dimensions. Okay, 512 D we will say 512 D. And why 512 for each word? Can anyone let me know why 512 features are we considering for each and every token? See, until now, each token, I mean, the sentence will be having a sentence. In that particular sentence, we'll divide it into tokens. And for each token, we'll do the embedding. Okay, embedding will be happening. And embedding, what exactly happens in embedding? A token ID will be assigned to each and every word, or else each and every token ID will be assigned. And each and every token ID which is assigned for the token will have its own 512 features. Okay, will have its own 512 features. Why 512? Each word will have 512 features. Okay, each word will have 512 features. Let me just write it over here. Let me just draw. So first, what it is, input sequence, right? Input sequence. Input sequence we're having. Then comes what? Then comes from the input sequence, what exactly happening? Embeddings, right? Embeddings. Embeddings. And in the embeddings, what exactly happening? In the embeddings, what exactly happening? We are the input sequence is being divided into tokens, and these tokens are passed into embeddings. And in the embeddings, for each token, the token ID is assigned. Token ID is assigned, and for each token ID, or else for each token or token ID will have 512 dimensions. Okay, we'll have 512 dimensions. Okay, we'll have 512 dimensions. What is this 512 dimension, and why exactly 512? Understood until now, and understood my question? Any confusion? See, these input embeddings are important to understand. Okay, positional encoding, all those layers are very easy. I see few S. What about others? Okay, fine. Okay, as your people are saying is, so what are those 512 dimensions? What are those 512 features? What does each feature say about that particular token? I just gave the answer also. So please try to answer. What are those 512 features representing for that particular token? My question is, I told for each token or the token ID, we have 512 features. Correct. So my question is, why 512 only? Why only 512 I told? And what are those 512 features doing over there for one single token? What are those 512 features doing over there for one single token is my question. Everyone understood the question? At least understood the question? Okay. Now I will say. So I was actually expecting an answer. It's fine. So you all know dimensions, right? You all know dimensions, right? One dimension, two dimensional, three dimensional. Correct. So, and up to how many dimensions a man can see? A human being can see? Yeah, up to three. So I just remember this. I just want to say this. So last week I was in Uttarakhand, and some person was saying that I can see six dimensions in a photo frame. He was trying to sell that photo frame to me. I just remember this when I was talking about these dimensions. He was saying that in the photo frame, I was able to see six dimensions. Okay, jokes apart. So coming into this dimensions part, okay, maybe that guy was able to see all these 512 dimensions, I guess. Okay. So token, token ID, 512 dimensions. 512 dimensions. So for one single token, I told a token ID and 512 dimensions. So now what each dimensions do is they capture the information about the meaning, context, and the relationships. Okay, they will capture the information about just remember this. They capture the information about the meaning, the context, the relationship with each and every word. Okay, I'll just write it down over here. Capture the meaning or information about the context, relationships, about to word. Okay, relationships or the meaning. So this is what exactly all those 512 dimensions are doing. All the 512 dimensions are doing this work. Okay, all these 512 dimensions or 512D are doing, trying to capture the meaning, the whatever the layers of NLP we have seen. There were around 7 layers we have seen, right? Whatever the layers which are applicable over here, each and every feature or else each and every dimension is trying to store the information about that particular token, the context about that particular token, the relationship it is having with the other tokens. Okay, all those things will be stored in the format of dimensions. Okay, each and every token will have 512 dimensions. And how those 512 dimensions are represented in one single array. In one single array, we'll have starting from 1 up to 512. Okay, up to 512. So each and every one dimension will represent one kind of feature. Okay, one kind of information. Each and every this dimension will have one kind of information about this token. Clear now? Clear now why exactly what is this 512 dimensions doing for one single token? Okay, fine. So my question is why only 512? Why only 512? So this one you can also say 512 is the size of a vector. Okay, vector. Vector size is 512. If someone says what is the, so I'll just say why 512 also. Why exactly 512 means 512 is the base. Okay, 512 is the base. In order to make sure that our model is not overfitting or else it is not assuming the things, we choose 512. Okay, we choose 512. 512 is the base. Okay, base dimension model for this transformers architecture. Even while developing this or else even while working on this transformers architecture paper also they have considered 512 dimensions only. Okay, we can say it as a size of a vector. So 512 is the size of the vector. Which vector? This token vector. Okay, or is this token ID vector? 512 is the size of the vector. So why not few dimensions or else high dimensions? See, we can get these questions. See, the researchers have considered 512 dimensions I told, but why not less or else why not high? This is a question. Okay, why not less than 512 or greater than 512? If you are considering less than 512, okay, if you are considering less than 512, the model will not be able to represent the meaning well. Okay, the model will not be able to represent the meaning well, because example, let me write it properly. Let's consider an example. So example, let's say that so the input query is something like, so we have trained, I'm having some paragraph. On that paragraph, the transformers architecture have been trained on. So I have asked a query, like the query is describe the person with two words. Okay, person with two words or two adjectives. Okay, so describe the person is the query. Let's say describe person. Okay, describe person. Describe the person. So if I just give this query, describe the person, and if I'm having less dimensions, less than 512, let's say I'm considering only 4 dimensions. Okay, I'm considering 4D, 4 dimensions. So if I just give this information like describe the person, it will give, it will have only 4 features. It was trained on only 4 different features. So it will just say about that particular person in 4 words, right? That particular person in 4 words. It will add some adjectives around, and it will describe about that particular person in 4 words. But if I am giving around 512 features, so it will make sure that it is describing about this person in detail and clear. We just told describe. It will make sure that it is telling about this person in detail and clear. Got it? Why 512 exactly? And 512 was the standard basic, okay? Standard basic, which is being used from a very long time. So more details will help the model distinguish between the meanings. Okay, whatever the query which you are asking, the more details will help the model to understand each and everything clearly. So that is why even the researchers were considering 512 dimensions or the vector size of 512 for each token ID. Understood until here? Understood until here, everyone? Okay, but why not more than 512? Okay, we can consider more than 512 also, but if we are having more dimension, let's say we are considering 10,000 dimensions, okay? 10,000 dimensions. So what exactly happens over there? There could be an issue of overfitting, and the training process also will be very slow because we need a huge computational resources, and it also requires huge memory. Correct. So these could be some of the challenges also if you're having too many dimensions. So in order to make sure that we are not introducing many dimensions or else less dimensions, we are going with 512. Okay, we are going with 512. And also there is this 768 dimension model also. Someone said birth, right? For birth, we are using 768, okay? And for GPT-2, there is this GPT-2 model also. Even that is built on 768 dimensions. And there is this BERT large, okay? BERT, BERT large model, which is on 1024 dimensions. Let me just write here. In the birth only, we are having a base model. And this base model is built on 768 dimensions, okay? 768 dimensions. And in the birth, again, we are having large, and this is built on 1024 dimensions. And before that, the GPT-2 is all have already been launched long back. GPT-2 small, and that works on 768 dimensions, okay? But the transformers architecture is built on 512 dimensions. So not as we are understanding the transformers architecture, so I have just considered 512 dimensions, okay? But one doubt you people should get, so please try to recall all the concepts. Try to recall all the concepts. I need that one single doubt. Okay, fine. For now, let's have a short break. Okay, let's have a short break. Be back here by 11:15. Okay. I hope it's clear for everyone. In the meantime, if you are having any doubt, the topics which we have discussed until now in this session, you may ask in the Q&A. Okay. Thank you. Let's take a short break, guys. Manya, I see that you're asking to share all the notes. So we'll be sharing a detailed handout, okay? We'll be sharing a detailed handouts in the documented format, okay? Not not the notepad notes, but we'll be sharing everything in a documented format, explaining each and every concept over there, okay? Don't worry. Yeah, you'll be getting the recordings of this lecture, okay? Please have a break for now. We'll discuss everything in the last 10 minutes, okay? Thank you. Okay, I hope everyone is back. And Devyansh, the session is for 2 hours, okay? Don't leave now. Okay? Let me just share this screen. Okay, I'm sharing my full screen. Now it will be much better. So this is the architecture, right? Now we have seen this input sequence, which is going into these embeddings, right? Sorry. So input sequence is being embedded, correct? So initially, how it is being embedded? Token embeddings, and for each token, we're having a vector of what is the size of the vector? 512, right? 512. And after that, we have linear transformations. Okay, linear transformation will be having, and then the attention score will be computed. Okay, the computing the attention score will be happening, scaling, and then the weighted sum will be calculated. Let me just write over here all those steps. Let me just copy these things. Let me just put it over here. Embeddings, right? Input sequence. In the input sequence, what are we getting? Token embeddings. Token embeddings. And once the token embeddings, in the token embeddings, what are we having? We are having this token IDs. Token ID. For each token ID, token ID, token ID, we have 512 dimensions, correct? And after token embedding is done, after the token embedding is done, we have this linear transformation. Okay, we have linear transformation, and then the computing of attention scores, linear transformations, computing the attention scores, computing the attention scores, and also we'll have scaling part of it. Scaling part later comes the weighted sum of values. Fine. In the embeddings only, all these things are happening. In the embeddings, all these things are happening, and in between, we will be having this positional input. Correct. So, what are all the four main key core components? What are all the four main key components in the architecture, in the PPT? We also PPT, here is the PPT, right? What are the key components? Encoder, decoder, positional encoding, and attention mechanism. So let me just write here. Key components. What are the key components? Encoder, decoder, positional encoding. And also, what is the last one, guys? What is the last one? Attention mechanism. Yes, this is very important. Okay. Attention mechanism. So these are the key components. Now we are discussing about this encoder. In the encoder, we see there is this. Before diving into encoding, we are having embeddings and positional encoding. And for the embeddings, the input will be the input sequence. This input sequence will be the text which we are giving. That will be going into the embeddings. And all this process happen in the embeddings. Okay, embeddings. The workflow input sequence, embeddings. In the embeddings, we have token embeddings. We have linear transformation. We have computing the attention scores process. And then we have scaling. And then we have this weighted sum of values. Okay. We're done with token embedding. Now we are going to discuss about this linear transformation. What exactly is this linear transformation? In the linear transformation, we have Q, K, and V. What is this Q, K, and V? Everyone knows how the dictionary works, right? Key value pairs. So Q, K, and V will represent the Q represents query, K represents the key, and V represents the values. Okay, Q query and Q, K, and V by multiplying. Okay, we create Q, K, and V by multiplying the embeddings. Just remember in the linear transformers, what happens is we'll create this query key and values. Okay, we'll create this Q, K, V by multiplying the embeddings. Okay, by multiplying the embeddings, and for each embedding, there will be a weighted matrix formed. Okay, there will be a weighted matrix formed. So weighted matrix in the sense how that will be weight of Q, weight of V, and weight of K. What are these weighted matrices? Weighted matrices. A query key and value. Okay. Now what's happening here? Now we will be computing the self-attention weights. Okay. Now we'll compute the self-attention weights over here. I hope you're understanding. Are you getting anyone? I mean, anyone having any doubts or issues? Not audible. Yeah, I'm audible right now, right? You understanding? No, I'm not getting what no exactly. You're understanding or else you're having doubt? No doubts. Okay, fine. Thank you. Thank you. Self, okay, self. Fine. So linear transform है linear transformation, what exactly it is doing is, I'll just say, try to listen. So first we'll create this q, k, and v. What is this q, k, and v? Query key and value. What is this query key and value? They are the vectors, okay? Query vector, key vector. Okay. What is this query vector? We'll see now. Query vector we'll say query vector, okay? We'll say it as a query vector. What is this query vector? It will help us to calculate the token, okay? It will help us to calculate the token and to understand the importance with the other token, okay? Mainly to understand the importance with the other token. The query vector will make sure that it will calculate and it will help us to calculate and understand the importance of the other token. Just remember this. What does a query vector does, and where does the query vector occur? This could be one kind of a question. So the query vector will be created in the linear transformations under the embeddings. And what exactly the query vector does is it will help us to calculate and understand the importance with the other tokens. Okay, fine. So now what is this key vector again? What is key vector? What does key vector do? It will help us to find the attention score with the tokens. Okay. It will help us to find the attention scores. Attention scores of what? Along with what? With the tokens. Whatever the tokens which we are having, for those tokens, the Q, K, V will be assigned, and the K will make sure that is finding all the attention scores, how much attention need to be given to that particular token. Each token will be having, right? We'll get to find the importance of that particular token, how much it is important, like understanding the context. It will play a key role in understanding the context to find the attention, and it will assign a score to it. For each and every token, it will assign a score as per the attention for what with the tokens. Okay, and value is nothing but the actual value after the word embeddings. Is nothing but the value over the actual value after word embeddings. Okay, this is for Q, K, and V. In the linear transformer, in the linear transformation, we create the Q, K, and V. Q is nothing but the query vector. K is the key vector. V is the actual. V is the value. And what does query and key do? Query will help us to calculate and understand the importance with the other tokens. What does key do? Key will help us to find the attention score with the tokens. And what does V do? V is the actual word embedding. But how that is happening? By using this weighted matrices. Okay, by using the weight matrices. Weight matrix. Okay. So initially we will be creating this Q, K, and V, and we will be multiplying the embeddings by the weights. Okay, we'll multiply the embeddings multiply by weights. Okay, we create them. We create query key and value. And then we multiply by the weights. We multiply by the weights. What weights? These weights. Weight of query, weight of value, and weight of the key. Okay. Weight matrices we'll be calling weight matrices or weighted matrices. We can let's write it weight matrices. Okay. And why are we doing this? To compute the self attention weights. Okay. To compute the self attention weights. how the self attention is to each and every token to compute the self attention. Just to compute the self attention. See here, computing the attention scores, that is happening over here. And how we are computing the self attention? So for each Q we have the particular value followed by the weight matrix, okay, followed by the weight of that Q. So similarly for K we will have K followed by X followed by W and K, correct. And for V also we'll have that X value in the weight matrix of V. So this is how we will be computing the each and every self attention for that particular Q, for that particular K, for that particular V. Okay. And what exactly is X over here? X is nothing but the token embedding. Okay, token embedding, or else the dimension which we have created for that particular token. The embedded token we are having it, the token ID with the 512 dimensions. So that is X, okay. That is X. Just give me a minute. Okay, I'm sorry. Fine. So what is X here? Token embedding, okay. Token embedded, where here we are getting the embedded token, right? In this token embedding. So that is what X is, okay. That is what the X is. And WQ, WK, and WV are the learned weight matrices. Learned weight matrices. These are all the learned weight matrices. So we have computed the attention scores also. Let me just remove this. Here we have started, right? Not here. After creating, we'll multiply by weights. So before multiplying this step, we'll be calling it as computing the attention scores. And then comes the scaling and weighted sum of values. So this computing the attention scores and also this linear transformation clear? 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 Any doubt? Okay, now I'm having it out. Can I ask? Okay. So what are these learned weight matrices? What are the learned weight matrices? And how the weights are assigned? Is there any specific weight which is assigned, or else how the weights are assigned? Now let me know how the weights are assigned. This is the question. Just try to think, okay? Don't use any Google or anything. How the weights are assigned over here? And what is this learned weight matrix? I just want to know that. Let me know. Clear, right? My question is. Okay, my query is not clear. Fine. See this WQ, WK, WV we are having, right? So we are saying computing the self attention weights. How the weights are assigned actually? Correct. I got the answer. Yeah, it is assigned by Q, K, and V. We will create them. But before creating, I mean after creating, for each Q, K, and V, we're having the weights, right? We create them and we'll multiply the weights. These are the weight matrices for each Q, each V, and each K. How these weights are assigned? Initially, they were randomly assigned. Okay. Initially, they were randomly assigned, and then through the back propagation, they learn. Okay. Through the back propagation, they learn. Correct. Correct, Arshdeep. Thank you. So, whatever the questions I'm asking in between, was it confusing or else I see only one person understood? Back propagation, we have discussed it in the ANN. I mean, in the last session, what did we discuss? Did we discuss about RNN and LSTM? Bit confusing. If I go into mathematical completely, it will be very much complex. So, I'm trying to explain it in a theoretical format only still, because we need to completely focus on generic. You need to understand what exactly happening here. See, for each, let me try to come up in Hindi. I'm sorry, I can't frame the words also. Okay, it's fine. I'll try to explain once again the flow, okay? Up to embeddings clear? Embeddings up to clear? Shishwant and also others. Okay. Now in the linear transformations, what is happening is for each token, array token will be having query, key, and value. Okay, query, key, and value will create. Okay, we'll create them. And how we are creating this Q, K, and V? How we are creating them? We are creating them by the weight matrices. For each token, three weight matrices will be applied. Okay, three weights will be applied for each token. That is query, value, and key. Okay, and how we are computing them? Like this, we are computing and getting the we are creating and getting the answer for Q, K, and V. Okay, Q, K, and V, we are getting the answer. How we are getting? By multiplying the weight with the input. And how we are having this weight? How we are getting the weight? And why we are doing this weight matrix? To compute the self-attention weights. Okay? For each and every token, what is that own self-attention? Okay, self-attention means its own attention, right? For each and every token, what is its own attention that we are calculating, and how we are calculating by assigning the weights. Initially, what we will do, see this. We start from randomly assigning the weights, and then while training, they are reassigned and used. I mean, reassigned, and how they are reassigned using the back propagation technique. Initially, the random weights will be applied. Okay, initially the random weights will be applied over this WV, WK, and WQ on the same token while we are creating this Q, K, and V. And while training, the weights will be reassigned and the weights will be adjusted. And that adjusting process is known as back propagation. Okay. And then we get it. Then we get it Q, K, and V with the learned matrices for each and every token. So for each and every token, we have query, key, and value. I hope it's clear. Okay, now let me know. Is it clear now? Somewhat, or else still any confusion? Just a moment. I'm sorry, guys. I got a call. I'm really sorry for that. Okay. So you want me to explain once again, Akshita? Fine. Others understood, right? Others understood. I'll just create a short poll. Let me know through the poll so that even I will be getting to know how much you understood. Okay. Yeah, and we are only left with last 10 minutes, so I'll just close it off up to here. Okay. Okay, let me know through the poll. In the meantime, who haven't understood, please I'll just walk you through the workflow. The complete Transformers workflow I will walk you through. Please see, okay? Please see. Let me just share the full screen also. See, we are discussing Transformers architecture, okay? In the Transformers architecture, we have input sequence, embeddings. Let me just pick another marker. Input sequence, embeddings, positional encoding, then encoder, decoder, and the output. Okay. And what is this input sequence? First, we'll start from the very basic. Okay. Input sequence is nothing but the input text that we are giving. Okay. And that will go into embeddings. So, what exactly happens in embeddings? And what are the different layers it needs to go in the embeddings? So, first input sequence will be divided into tokens. Okay. Input sequence will be divided into tokens, and that tokens will be passed into embeddings. In the embeddings, we have token embeddings. Okay, token embeddings is nothing but for each token, the token ID will be assigned. And along with the for each token, the token ID will be assigned. And for the token or the token ID, we have a vector size of 512 dimensions. Okay, we have a vector size of 512 dimensions, and each dimension will represent any one of the feature. Okay, and then we have this linear transformations. And what happens in this linear transformation? We have this. We create query, key, and the value. Okay, query vector, key vector, and the value we will be creating. What is this query, key, and value? Query will help us to calculate and understand the importance of the other tokens. And key will help us to find the attention score for the tokens. Okay, attention score for the tokens. And value is nothing but the actual value for word embeddings. But how that Q, K, and V are calculated? Initially, a random weight of query, random weight of value, random weight of key is assigned, okay, is assigned and it is computed. How it is computed? To that particular token only it is computed. To that particular token only the weight is computed for query, key, and value. And that computing we will be calling it as self-attention weights computing. Okay, computing the self-attention weights. That process is known as. And we'll get the Q, K, and V values. How? Initially, random weights will be assigned. After the random weights, the weights will be adjusted as per the training. And then we'll be getting a K, Q, and V. Okay, Q, K, and V will be getting. And this X of V, X of WV, X of WK, X of WQ, nothing but the self-attention weights. Okay, self-attention weights. And what is X here? Token embedding. Okay, X is token embedding. WQ, WK, and WV are learned weight matrices. Okay, learned weight matrices. Here we do the scaling. This is the weighted sum values next, which is coming up. And later we have this multi-head attention. Multi-head attention is very important. Okay, if you see in the architecture, we are left with this positional encoding, multi-head attention. This normalization is nothing but standardization and normalization. MLP is nothing but the multi-layer perceptrons. This is what the whole encoder architecture is. Then again here we have we'll get to know about this masked multi-head attention, and this normalization again are the same, multi-head attention are the same. MLP is again the same, multi-layer perceptrons only. And we'll discuss about this softmax. Here we have the logits also. We'll be discussing all these things in tomorrow's session. Okay. Clear, confusing? Okay, thank you, Vansh. I see 8 no's. Can I get to know what is the issue? Is that clear, Akshita? Okay. I still see 8 no's. I need a confirmation on that. When will previous and the current lecture be uploaded? It will be uploaded, girl. I will just inform the team. Okay, don't worry, please. Okay, got it. If you go into the mathematical part, it will be more complex, but it will be completely clear. Okay, it will be a bit more complex, but it will be completely clear if you go into the mathematical part. I'll try to make sure I'll involve that mathematical part tomorrow. Okay. So in the meantime, if you are having any other queries related to today's session, please ask. Okay. Thank you. Okay. Now, Devansh and also Aryan, you may leave. Okay. Yeah, even others can leave. Thank you for attending the session. Thank you. Thank you, Aditya. Thank you, Yash. Thank you, Aryan. Thank you, Mana. Thank you, Shreyasi. Thank you. Thank you, Shivansh, Manish. Okay. Thank you, plus one. Okay. Thank you. Okay. Thank you, plus one from my side. Yeah. Have a great day. Have a great day, guys. Thank you, Vansh. Thank you. Yeah, I will take it. Thank you, Aditya. When you people take care of yourself, okay? Thank you. Okay. Fine. Okay, guys, if you're not having any queries, you may leave. I'll just end the session. Shesh. Abhiram, you can start with this intermediate level, okay? In the GCP, you'll have this intermediate level. Okay. If you're done with beginner, you can go for intermediate level. So once you are saying that is it related to gym you're saying? Chest day? Thank you. Okay, I'm ending the session, guys. Thanks for joining. And remember, even tomorrow also we are having session for 2 hours, okay?